Lecture 2.3a, Continuity. Now that we've studied limits and we understand how they work, it's time to see why they really matter. And that involves a concept called continuity. By the end of this video, you should be able to determine whether a function is continuous at a point or on an interval, and you should be able to categorize types of discontinuity and extend functions so that you get rid of these things called discontinuities. First, I want to reference something we talked a little bit about in class. Real-world functions are really the reason calculus exists. Calculus is a mathematics field that was invented to solve problems. Unlike other types of math which just describe the world around us, calculus is a tool. And it's a tool primarily to make predictions. For example, for thousands and thousands of years, people needed to be able to predict the tides so that they could sail places. Or more currently, we would like to be able to predict how the Ebola outbreak is going to proceed so that we can make sure that we're prepared for what happens. And also for thousands and thousands of years, these predictions that we made could all be described by these connected functions. Functions where the lines kind of are smooth or crooked, but essentially every dot on the graph is connected to another one. And then in the 1920s, things changed. And as scientists started to understand the atom, they discovered something that's fundamentally different than any other natural process we had ever discovered before. If you look at how the energy level of an electron proceeds, as you start to heat up that electron, instead of smoothly changing the amount of energy it has, it makes these dramatic jumps. And all of a sudden, even though scientists didn't know how important atomic theory was going to be to the future of history, really, they knew they had discovered something crazy different because of the way it behaved, because this graph is not connected. This is a natural phenomenon that's somehow different from all these other ones. Well, that idea, that not connectedness, that's basically what continuity is. We can talk about continuity at a point or on an interval, or we can talk about a function that's continuous, but regardless of what level you're talking about, basically, continuity is the idea of being connected. So there are parts of this graph that are connected and parts that don't seem to be connected. Let's be a little more precise. Here's the definition of what it means to be continuous at a point. Notice that we label the point C, so we tell you what the x value is. Go ahead and pause the video, write down these definitions, and in the left-hand column, make a note. What do you think these mean? You probably are going to have to make some sort of comment about the difference between interior and bounded. And think a little bit about f of c. What does that mean? Right, so hopefully you were able to interpret the meaning of this limit. It's basically saying if the right-hand limit and the left-hand limit at a certain x value both equal the actual y value of the function, then we say that f is continuous at that x value. Now, if you remembered correctly, an interior point just means a point inside the domain as opposed to one that's on the edge, which is a boundary point. So the second part of the definition is just saying on the edge of the domain, so the two ends of the function, if they stop at a certain point, that point's only going to have either a right or a left-hand limit. And if that one limit equals the actual y value, then it's still okay to call that point continuous, even though technically it doesn't have both sides equaling that value. Let's see if you can put this definition to work. Here's a pretty simple function. It's actually the one that we saw a couple minutes ago. And using the interpretation that I just explained, I want you to tell me, is this function continuous at each of these x values? Now, there'll be a different answer for each x value because you're looking at a different point on the graph. Great, so you probably can gather the answers from Edpuzzle, but here they are. And let me just model the thinking process really quickly. I'll use -2 first. So what I would do is I would go to -2 x value, and I would look at the function, and I would determine three things: the right-hand limit, the left-hand limit, and the actual function. This particular x value, it looks like the right-hand and the left-hand limit are both approaching -1 as its y value, whereas the function itself equals +1. And since those things are different, that's why it's not continuous. At 0, for example, that's not true. The right hand and the left hand and the actual value of that point are all 0, and they're all the same. That makes it continuous. Pay attention to the boundary points. These boundary points, which is -4 and then 4.5, they're the edge of the function, so they only have one side. This one has a left side, this one has a right side. As long as that one side equals the actual value, it is continuous, so that's why the first one was continuous. Whereas if that one-sided limit does not equal the value, the function's actually undefined right here. That makes it not continuous. That's the explanation for 4.5. Okay, hopefully this is still pretty simple. You're used to looking at graphs like this by now. We can be more precise though. When a function is not continuous, we call it discontinuous, or we say that it has a discontinuity at that x value. And there are a bunch of different kinds, and you need to memorize what they are and what they look like. A removable discontinuity is what you are used to calling a hole. And it can be a hole that's just an empty spot or a hole with a y value somewhere else. Either way, we both consider these the same situation, basically. A jump discontinuity is one of the 3 non-removable ones, and it's when, as you can see, the function jumps, so the one-sided limit doesn't equal the other. Oscillating is a word you need to know now. This is also considered a discontinuity. This x value, whatever it is in the middle, doesn't have a limit because it's going back and forth and back and forth and back and forth, oscillating. An infinite discontinuity is when you don't have a limit because the two sides are going either to positive or negative infinity. These 4 types of discontinuity, removable, jump, oscillating, and infinite, are terms that you need to memorize. Take a moment to make sure that they are in your notes and that you understand them, and then we'll practice applying them. Great, here we go. So here's a pretty simple function. What you need to do is look at each of these x values and determine what type of discontinuity, if any, the function has. As before, you probably saw the answers in Edpuzzle. Here they are so that I can reference them, and I'll just talk through the reasoning for a couple of them. Now, one thing is some people struggle with looking at lines that don't have points. So at -4, you can see the point there, and you know that f of x is -2, and that it's the same as the two-sided limits. But the same thing is true at x equals 0, and there's no dot there, but we can treat it just as if there's dots. So if you were confused about this one, it's continuous because it's really the same situation as -4. We don't have to put that little dot there. For the discontinuous ones, this is removable because the sided limits equal each other. This is jump because the sided limits don't equal each other. And this is infinite, obviously, because we have a vertical asymptote. So far, we've been talking about continuity at a point. But I reminded you at the beginning that there were 3 different ways we could talk about the word continuous. So here's the second one. We say that a function is continuous on an interval, and a and b are going to be numbers, and it can be open or closed parentheses. But we say this if the function is continuous at every point in the interval. For example, what if I wanted to talk about the interval from -6 to -2? On my graph, this interval is always going to represent x values. So this interval is talking about the part of the graph that's between right here and right here. So looking at the graph first, this section of the graph, do we see any discontinuities? Nope, I don't see any. So my instinct is that yes, it's continuous. The one thing I should always check is the endpoints because they can be a little weird. This endpoint right here, -6, since it's a square bracket, has to be included. And sure enough, at -6, it's continuous, no problem. At -2, however, this is technically not an endpoint of the domain. The domain is continuing everywhere here. And so at -2, we actually do have a discontinuity. And that's because from the right-hand side, the limit looks like it's going to positive infinity, whereas from the left-hand side, the limit looks like 3. So actually, the first one is false. It's not continuous on the interval from -6 to -2 with a square bracket. I could change it really easily if I changed it to be a circle bracket, which means I wasn't including the -2, then it would have been continuous. Take that idea and see if you can work out these four. So as you just saw, actually, this function isn't technically continuous on any of these intervals. Some of them are just slightly off, so let's take a look at why they're all wrong. I already talked about -6 to 2, and the problem was at -2. If I had changed this interval to be -6 to 2 with an open point at 2, this one would have been continuous. That one would have been okay, but this one wasn't. From -4 to 0, we are crossing this point at -2, which has an infinite discontinuity and a jump on one side. So that's clearly just not right, and there's nothing you can really do simply to fix this one. Similarly, this one includes -2. If I had changed it to an open circle, the open circle from -2 to +4, that's actually fine. It's continuous that whole way. From -2 to +6, -2 is now not included, which is good, but actually 6 is a problem as well. So technically with the square brackets, that's no good. Similarly, this one's no good also because of 6, whereas if I changed it to this one would have been continuous. So the last thing we need to look at is equations. All of these graphic skills are really just a tool to help us understand what an equation is telling us. So we're going to look at equations, and we're going to ask the question, at what point is this function discontinuous, without knowing what the graph looks like? Look at the first example. I've got a cubic divided by a quadratic. It's going to be some weird rational function. I want to know where could there possibly be either a whole or an asymptote or an oscillating problem. Well, it's actually pretty simple. If you think about it, the only way something weird is going to happen with this function is if the bottom equals 0. And if you factor the bottom, it's a difference of squares, I can see that the two x values I might be worried about should be positive and -3, because plugging in either of those x values will give us a 0 on the bottom. Now, you know what polynomials look like, and rational functions are just divisions of polynomials, so there isn't going to be any oscillating situation. Possibly there's a vertical asymptote. If there is, it'll happen at one of these two places. What I need to know now is whether this discontinuity is a removable one, as in a whole, or one that's not removable. And the way we're going to tell is by looking at the y values. So I'm going to go to my graphing calculator and create a table to figure out whether the limit exists. If the limit does exist, then this is going to be a removable discontinuity. Let's take a look. So when I put it into the graphing calculator, these are the tables that I got. And what you can see is that at -3, this limit doesn't seem to exist. One side is going to -infinity, the other side, as we get closer to 3, is going to +infinity. But at 3, the limit does look like it exists, because on both sides, as we get closer and closer to 3, the limit seems to be approaching 3.33333. So I would say f of x has a removable discontinuity at x equals 3. And that's because the limit from the right equals the limit from the left, and they both equal this number. So if you think about it, this function by itself doesn't have is not continuous at 3 because of this removable discontinuity. Well, the whole point of being removable is that I can write a new function, and we're going to call this new function the extended function. It doesn't matter what letter you use. And basically for the extended function, we're going to use the normal function rule, which is x cubed minus 7x minus 6 over x squared minus 9. And we're going to use that rule for all x values except for 3. When x is not 3, that's going to be the function. When x is 3, and this is kind of like plugging the hole, we're just going to decide that y has to equal 3.333 repeated. And this one point that I'm adding to the function, think about having a hole. Well, it's like I'm adding in a point right here to make the function continuous. You've got 2 to try, and we'll talk about the answers to them in class, but give them a good shot, and then we'll talk.